Okay, so this session is on smart contracts. We're going to generally cover the topic of smart contracts, their history, the various types of smart contracts from a technical point of view and from an implementation, as in who in the market is actually offering them and what the advantages and disadvantages are. We're also going to look at conditions under which a certain type of smart contract might be advantageous to a specific type of application. So, Sam, over to you.
Yeah, so the term smart contract originated by a law and computer science professor named Nick Szabo, who began writing a series of papers about this concept in the 90s. And I'd like to briefly dive into some of his thoughts on that and explain how that has influenced the recent resurgence and interest in these ideas, particularly with respect to blockchain technology. So, as we discussed in the previous sessions, blockchain technology is a new technology that came onto the scenes with the Satoshi white paper and with Bitcoin, whereas smart contracts precedes that idea, by several decades. And the idea of smart contracts, as proposed by Nick Szabo, was really the idea of taking what individuals, when they enter agreements with each other on pen and paper, contractual agreements, and then enforced through the judicial system. The idea there was taking those agreements and in some cases the entire agreement, in other cases parts of the agreement, and encoding them as computer programs that would enforce the agreements of the contract in computer code. You could reduce a lot of the risk, the counterparty risk, and the efficiency, the transparency, and in some cases avoid having to go to the judicial system in order to enforce the contract to begin with. And he was interested. Nick Szabo was also a lot of his ideas ended up being incorporated within the cypherpunk movement. So this was the group of individuals in the mailing list that Bitcoin came out of, and Satoshi posted his work on originally. And a lot of these folks were very interested in the idea of taking pen and paper legal contracts, modeling them in computer code, and then enforcing those in computer code somehow. Now, there's a great paper that Nick Szabo did, and he's done a few great papers, but in one of them he describes what he calls a humble predecessor for smart contracts being the vending machine. And I think that's a good example. It kind of illustrates some of those ideas. But traditionally you would go up to the store and you would engage in a transaction and provide cash, and then the seller would then provide the good and then give you break the bill and provide you the change. And the vending machine really automates that. And it's not exactly a smart contract, primarily because a lot of the ideas behind smart contracts involve trust. And in a vending machine, in that idea, in that concept, you're still when you go and you purchase your Coca-Cola or whatever, you're still trusting that the vending machine is going to do what it says it will do. And I think the smart contract concept is broad and starts to explore not having to trust third parties and having the counterparties to engage in these transactions in an automated way, like a vending machine. In many cases, it is financial. It involves a transaction where someone is paying someone else for something, for some good or service. But then also, though, there's this other piece where you don't want to have to go through a trusted third party to engage in that transaction, because then you're essentially you lose the visibility, the efficiency, that these benefits that the ideal of a smart contract could provide. And so it really, the concept really started with Nick Szabo. There were similar ideas in the late 90s. Ian Grigg, he developed a concept called Ricardian contracts, where legal documents, and you would take parts of the legal document, like in the file, let's say it's a PDF of your legal document, and you would include markup that describes the parameters to the contract. So this is similar going down the path of how ISDA has standardized FPML for defining their interest rate swaps and financial derivatives. It's sort of that concept where you would have an existing legal agreement, still in English prose, let's say, but then attached to that English prose legal contract is a little bit of code or a little bit of markup that describes the parameters of the contract in a way that could be subsequently processed by a computer program. So it's not as extreme as Nick Szabo's concept of where the whole contract is possibly automated. This is more making contracts connect into computer systems and be easily read by computer systems, and extracting those parameters so that you could do, for example, accounting is one that's discussed a lot with Ricardian contracts. So you could have your accounting system consume these PDFs, let's say, of English prose along with these parameters, and it would extract out those parameters and then make decisions based on that, either recording the transaction or triggering a payment, that kind of thing. So that was in the late 90s. So you see Nick Szabo in the early 90s and Ian Grigg in the late 90s exploring these concepts. But really the missing piece was how to execute these smart contracts, these contracts without the requirement of a trusted third party. And that was really sort of an unsolved problem that hadn't been cracked. There were some folks. There was a project called Askimos there was the peer-to-peer technologies that come in waves. It kind of goes from so in the late 90s, early 2000s, there was a lot of excitement in peer-to-peer technologies. You had things like Napster, BitTorrent. We can do another session on that. But then it kind of it fell out of vogue, and then there was a resurgence over the past few years. But in that first, not necessarily the first wave, but in the 90s and early 2000s, there was a project called Askimos, which also explored like Nick Szabo's concept of smart contracts, and started to explore how you could have people that without a trusted third party execute a smart contract. And it's really like the Askimos project in the late 90s. Sorry, that was 2002, early 2000s. Was really a predecessor for some of the blockchain concepts, especially the permission blockchains that we see today. But it still wasn't. No one really cracked how you can easily have multiple participants engage in a smart contract without a trusted third party. That was still an unsolved problem, and even though the concept of smart contracts had existed for a while and people were very excited about its possibilities, no one had really solved that in an elegant way. Then Bitcoin showed up on the scenes with Satoshi Nakamoto's paper we talked about in the last session, and that paper introduced a peer-to-peer payment system, Bitcoin, and the currency where you could transfer funds from one from one person to another, pseudo-anonymously, it's coming out of the cypherpunk movement and possibly inspired by Nick Szabo's some of his ideas on smart contracts. Bitcoin introduced the concept of Bitcoin scripts. So in Bitcoin, although we describe it as Sam transferring 10 Bitcoin to Hossein, something like we describe it as like financial transactions where one person is sending funds to another person. The system actually supports more advanced functionality than just simple payment transfers. So there's actually in Bitcoin a scripting language, which is a small. It's a small computer program. It's not a fully general computer program. You can't have your scripting program do AI or anything like that. But it's really kind of basic in the sense of you have a set of operations your scripting language can do, like for example, check if this message has been signed by someone who has a private key for this public key. So checking that a signature is valid. That kind of operation is one of the operations in Bitcoin script, and Bitcoin lets you compose these operations in your transaction that you create. So I would say like 90% of all the Bitcoin transactions are just one type of script, which is kind of the vanilla generic kind, where it's someone consuming one party consuming a number of inputs. So they've been sent they own, and then those are inputs to their transaction, and they're sending an output to someone else. So if I was sending funds to Hossein, my script would specify these 5 inputs of coins that other people have sent to me, and then I would have an output that sends it to that has an output specifying that the coins go to Hossein, and then there's a fee, and as part of that, depending on the amount I'm sending, there might be coins that I send back to myself as part of that transaction. And most of the transactions in the Bitcoin network are of that basic form. But the important thing is that the Bitcoin network and protocol has functionality for doing other scripting. So you can get their signatures. So you can say that a transaction, just taking a step back. So transactions, we started to explain this a little bit in the earlier session. But in Bitcoin, transactions have inputs and outputs, and when you specify when you the user are creating a transaction and sending coins to Hossein, when you specify an output, in that output you actually have a condition that says only someone that can satisfy this condition can receive these coins. So generally it would be, I'll be sending coins to someone that has who can sign a message, who has a private key for a specific public key. It's a little more complicated than that. It's actually a hash of a public key, but your output would say only someone who meets these conditions can receive these coins. And so that's expressed in this Bitcoin script language. So in the transaction for that output, it would say, Hossein needs that Hossein or this person with this public key is the only person that can receive these coins. Now, you can do more complex things in Bitcoin script, like this multi-signature, multiple signatures, so that in order to spend the coins, you can do things like 2 out of 3. So you can specify 3 when you create your output. You can say these 3 public keys. 2 of the 3 public keys that I specify, any 2, need to sign a message in order to receive these coins. So you can think of that as the M of N type of transaction, where you need to have a certain number of signatures in order for the transaction to be valid, and you would express that in Bitcoin script. the same way, using the same mechanism, the same kind of scripting language you would use to do a traditional payment in Bitcoin script between two parties. So Bitcoin script doesn't really go much beyond that kind of functionality where you're checking signatures, you're specifying the conditions in order for someone to receive to spend the output. You can do things like multiple signatures. There's a lot of work going on right now in the Bitcoin community on expanding that scripting language. But for the purposes of this discussion, it's pretty much at that level. Now, so briefly jumping into the permissioned, so Bitcoin is a permissionless blockchain. There is a permissioned distributed ledger technology called Corda that is heavily inspired by Bitcoin. And this is a project being developed by R3, and Corda uses the same transaction model that Bitcoin does, where users create transactions. They have public and private keys. They sign their transactions, and the transactions that they generate have specified inputs within the transaction. So and then has the signatures, let's say, in many cases that allow that input to be spent, and the transaction also specifies outputs in the same way Bitcoin does, where the output has the conditions in which the output can be spent. And so Corda uses that same model instead of this very basic Bitcoin script language. Corda uses a language. So Bitcoin script. Bitcoin script is. So unlike in Bitcoin, where Bitcoin has their own custom scripting language to do these basic transaction conditions for payments, Corda uses a different scripting language that's written in Kotlin, which is a new language that runs on the Java virtual machine, but it allows you to write create transactions that have conditions written in this Kotlin language, which boil down to expressing the conditions of a transaction to be valid in terms of a logical formula. So you have predicates, and these predicates have to be when you create a transaction, when you specify the inputs, you need to provide the right solutions to the predicates in order for the logical formula to be valid and allow you to spend that input. So it's the same type of approach as in Bitcoin, where you have transactions, inputs and outputs. You have Bitcoin script to express the conditions of those inputs and outputs, and that's all included in the transaction, and it's modeled around payments and transfer, or in Corda's case, not just payments. It could also be just ownership of an asset. Let's say who owns this asset. It doesn't have to be necessarily be a coin. And then transferring ownership of this asset from one or more people to another to another person or another group of people. In the case of like an M of N type of transaction. So you can think of it as a very specific type of smart contract that involves financial instruments where someone owns and then transfers the instrument to someone else. In Bitcoin, it's Bitcoins. In Corda, it can be other. You can model other digital assets, and then expressing conditions on who can transfer that and who can spend the coins or transfer the asset. So that's the model that was introduced by Bitcoin and Bitcoin Script. After Bitcoin came out, Vitalik Buterin, who was a journalist at the time for one of the prominent Bitcoin magazines, he was really excited by the idea of this Bitcoin Script functionality, and he wanted to expand it so that instead of just these payment-related conditions in the scripting language, he wanted it to be much more general, where you could have transactions that were really that met the full vision of smart contracts, where you could have any kind of computer program being run on the blockchain and express any kind of conditions, not just M of n or these kind of basic cryptographic kind of conditions of this person has his private key or something like that. You could you could do things like, he wanted to be able to express smart contracts and agreements for things like, for example, being able to have a payment that's conditional on some outside piece of information, like if you look at sports betting, for example, if being able to do a payment based on a condition of who won a horse race, that kind of thing, or having a smart contract among a number of players where certain people get paid based on a condition from some outside world event, and being able to have logic in there and more expressive conditions, more akin to the kind of contracts you see, the pen and paper kind of contracts you have. And so he proposed Ethereum, the Ethereum network, and they adopted a new type of transaction model that allowed you to express what Vitalik calls these Turing-complete smart contracts. Turing-complete, all that means is that instead of being a limited programming language of conditions, you can write you have a programming language that can do arbitrary computations. So a Turing-complete machine theoretically can do any kind of calculation, any kind of computer program. Now, of course, there's limitations on that, so Ethereum was born, and they adopted a new transaction model, and in that transaction model, instead of transactions specifying inputs and outputs, in the Ethereum case, you would develop your smart contract in a programming language. In Ethereum, it's called Solidity. There's a few other programming languages you can write in for Ethereum. And the Ethereum network runs what they call the Ethereum virtual machine. All that is a system that executes smart contracts. And so you, as a smart contract developer, would write the code for your smart contract, and then you would create a transaction that would deploy this code to the Ethereum network, so to all the nodes running on the Ethereum network. And then this code would be available sitting there, and you could create, other folks could create transactions and send messages to that computer program, to that smart contract. And so every smart contract deployed on the Ethereum network has a unique identifier, and you create transactions that specify that unique identifier and include a payload, which is information that the smart contract will then receive and process and make a determination that could be, in Ethereum, there's a cryptocurrency attached to Ethereum called Ether, and it could be transferring Ether, like you could transfer funds between two individuals as part of that logic. In the case of, we had the horse race kind of sports betting case, the winner would then, you'd have a number of participants put their funds in escrow, and then the winner would then receive you do payouts based on the results of the race. Yeah, that's the basic model. It's a totally different transaction model. So instead of, like we're in Bitcoin, each transaction had the inputs and the outputs, and you had this Bitcoin script inside the transaction specifying the conditions on who could spend an output. In Ethereum, you write your whole smart contract as a computer program. So it's a bunch of code. You create a transaction that deploys that and sends it to the network, not to like an individual. There's no inputs or outputs. That code, once it's deployed, or you can think of it as being installed on the entire network, is now sitting there waiting to receive transactions, and then people create transactions that send messages to that smart contract based on a unique identifier. So it's a very different model. Your transactions don't have inputs and outputs. The transactions don't have, they don't specify the conditions in the transaction. So in Bitcoin, every transaction has the conditions on who can spend it, who can spend those coins for the inputs, for the outputs, and for the inputs it specifies the information, the signatures, so that you show that you are allowed to spend those coins. In Ethereum, that's not the case. So in Ethereum, a transaction has a payload. It's just a bunch of data, and the transaction receives that, or the smart contract receives that payload and determines whether or not the transaction is valid by executing it in this Ethereum virtual machine. Now, this is a computationally expensive process. So you also have to, smart contracts in the Ethereum network need to be funded. So you need to provide Ether. You need to send Ether coins into the smart contract, which pays for the network to run these computer programs and process the transactions. But that's the gist of it. It's a very different model, and it moves us closer to the dream, the Nick Szabo dream of general purpose, smart contracts, like pen and paper contracts that are now being automated by computer programs. Now, to move on to the next technology. So Hyperledger. So Ethereum is a permissionless blockchain technology that supports these smart contracts. Hyperledger Fabric was sort of in a similar way that Corda was inspired by Bitcoin. I would say Hyperledger Fabric, a lot of those designs were inspired by Ethereum. And similarly, in Hyperledger Fabric, which is a permissioned blockchain, it's a private blockchain, you have a similar transaction model where a developer writes their smart contract in code, they create a transaction that deploys it or installs it on the network, and then participants in the network they create transactions that send information to that deployed smart contract in the same way as in Ethereum. Except in Hyperledger Fabric, instead of the programming language being Solidity or the Ethereum virtual machine, Hyperledger Fabric supports other programming languages like Go and JavaScript and Java. And there's some technical differences too in the transaction model, but we'll get into the details of that in another session. So advantages and limitations of smart contracts. So the dream of smart contracts and the advantages is to reduce counterparty risk, increase transparency, and improve efficiency of processes that were traditionally performed with pen and paper contracts. Now, you can't you can't take any. Smart contracts are limited. I mean, they're computer programs. They can't do everything that a pen and paper contract from the legal world can do. There are plenty of contracts that will go through years in the courts, like trying to determine whether or not they're valid or whether or not people met the constraints of the contracts. And this technology can't totally replace the legal system as it is now. So smart contracts today are really only applicable to specific types of pen and paper contracts or contracts that are suitable for being modeled as computer programs. So a good example of this is the work that ISDA has done with FPML, where they've come up with standards and specifications for interest rate swaps and derivative contracts that are very clear, and they have agreed. There's a standards body, and a number of different organizations have agreed on what can go into a derivative and how to express that in code or in a data format, FPML. And that type of thing where it's already been digitized, there's an overarching legal framework around it, in the master agreement, is very suitable for smart contracts because it can allow, let's say, execution facilities, let's say, to process these digital contracts by writing a smart contract in a blockchain, let's say, without requiring a trusted third party. So you can gain those transparency, reduce the counterparty risk, and improve the efficiency because you no longer need to go through, the participants don't need to have to agree on a trusted third party to process the transaction on their behalf. Now they can do that directly by writing a interest rate swap, let's say a smart contract. So you gain those advantages, but it's not universally applicable. Now there's a lot of technical details here regarding on the limitations of smart contracts, which we can't go into today due to limitations of time, but we'll certainly explore from a practical perspective when you're writing a smart contract what you can and can't do. We'll do that in a separate session that goes into things like non-determinism, making sure your smart contracts don't stay in a loop and just never complete. They need to terminate. Things like that, which it's a much more technical discussion. But big picture, there are certain pen and paper contracts you can model as computer programs. You can execute them amongst organizations who are semi-trusted or untrusted without the requirements of a trusted third party. And that brings about transparency, improved efficiency, and reduced counterparty risk over the traditional pen and paper and legislative kind of framework and pen contracts that are being deployed or employed today. Now, if you have an application that is financial related and the participants are totally anonymous and you need it to be tied and it's all payments related, then technologies like Bitcoin and these blockchains and the scripting language are probably what the right thing that you need. If you're looking for applications where the participants are known ahead of time, and the application's also payments or financial related, some kind of financial instrument, or maybe perhaps things like a title or some kind of token that represents some real world asset, and the transaction logic is on the level of does this person have this private key, or do 3 of the 5 people sign off on this, that kind of logic, that kind of sophistication, then a permission blockchain like Corda might be more appropriate in that type of scripting language. If you need to go do things like we explored the sports betting use case on Ethereum, where you have anonymous participants that are betting on the results of a horse race, and you're dealing with cryptocurrency payments. And then Ethereum and that type of model is probably the most appropriate choice. And then if you're doing permissioned blockchain where you have a permission network where the participants' identities are known and you have to be approved in order to gain access to the network, and you're going beyond basic payment conditions. So you can for example, insurance claim processing, where you have insurance companies and suppliers on networks that are processing claims between them, and you have conditional logic to validate those claims. And it can also include payments. You might be triggering payments when certain conditions are met. Then a technology like Hyperledger Fabric is probably the best fit for that. So, given that we're almost out of time here, I'd like to wrap things up and see if there are any questions.
Great. Sam, thank you so much. This wraps up the introduction to smart contract. Next week, we can discuss in further detail the benefits of smart contracts in various formats and the other topics that are included in the series. Thank you.